I'm going to let him go on and explain what he does because I know he's going to be able to explain it much better than I would. So I'll go ahead and turn it over to him.
Okay. Hey, good morning, everybody. For the next minute, it's still morning. Thanks for having me here. It's not my first time speaking with high school students. Can everybody hear me okay?
Oh, Coach Abney. There we go.
Okay. So anyway, it's not my first time speaking with high school students, but it is my first time doing this virtually. So if I'm like stuttering or if you have a question that you'd like to ask, I'm actually very comfortable with you just interrupting me in the middle of my presentation to ask a question, although my plan is to provide time at the end of my talk to have more of a dialogue with everybody. So without further ado, I'll figure out how to share my screen and we can just jump right into a couple of slides that I have prepared just to overview some of the work that I do. Slideshow view. All right, so as mentioned before, I'm an engineer. I'm specifically a mechanical engineer. There are many different disciplines of engineer, and in fact, the term engineer is thrown around pretty liberally across a lot of different job categories. But a mechanical engineer is sort of the jack of all trades. We'll just jump right into my background, and then we'll get into the meat of some of the stuff that I do. So I have more degrees than is really necessary for any of you who may be interested in engineering. I got my undergrad at University of Maryland, College Park. I grew up in Maryland, so I went to a nice state school, good engineering program, pretty inexpensive. I got my master's degree at Johns Hopkins while working, and I also put that was free. One of the nice things about STEM is if you're interested in pursuing advanced education in those fields, there's often a lot of funding available for those types of things. So that was nice. In terms of the master's degree, my work paid for that. I'm currently at Georgia Tech. I was in aerospace. I'll talk a little bit about that in the next slide, but I'm currently finishing up my PhD program. I've been picking up an MBA as well, because after this, I don't want to go back to school again. But the PhD program is also free. The reason being that, again, in STEM, it's very common that you will be awarded grant funding, or your advisor, your PhD advisor, will have their own funding to support tuition. It comes with a living stipend. So generally, if you decide to pursue STEM, there's a lot of support for education. In terms of jobs, as I mentioned, I worked in aerospace for a company called Northrop Grumman that was up in Baltimore. Mostly we worked on radar and sensor systems. I'll go into that in a little bit. Currently a grad researcher, and next month when I graduate, I'll be a product lead for a medical device startup company here in Atlanta. Just to round myself out a little bit more, I do have more broad interests. I want to emphasize that there isn't really a stereotype for engineers. I know it's really common to think of us as being like really nerdy, math-oriented people, socially awkward loners. That's really not the case. I think when any of us consider stereotypes, it's very quick, especially ones that may have been applied to ourselves. It's very easy for us to pick out ways that we deviate from that, and this is no exception. So engineers we fit every category of interests and activities, and these are some of mine. So I'm really interested in sports. I like fixing things, taking them apart as well, but mostly fixing them. I'm interested in dogs, gaming, and then weird nerdy fact, economics as well. But just jumping right into some of the work that I do. For Northrop Grumman, this was most of my time spent as an individual contributor engineer. And as a mechanical engineer, if you have a notion of looking up what a potential curriculum might be for an undergrad degree at a university, you'll find that the subjects that you study are very, very broad. You sort of learn a little bit of everything. And that's because mechanical engineers are placed in pretty much every industry you can think of. We're involved in materials science, we're involved in aerospace, electronics, chemical, you name it. And when it comes to the sort of meat and potatoes of mechanical engineering, what we do is we take really interesting and cool ideas, and we make sure that you can actually deploy them in real life, in the real world. So for example, If an electrical engineer designs a really cool like radar system, really neat circuit boards, well, mechanical engineers are required to figure out, okay, how are we going to build it? How are we going to protect it from the environment we're putting it in? Is this going to be on a Navy ship where, for example, salt water is very corrosive for metals? So we need to protect our metal, protect our electronics with special coatings that we use. We do a lot of 3D modeling and simulation, whether it's for thermal management or just to figure out how assemblies will be put together before we actually go try to do it, generally because it's cost saving and time saving as well. So I touched a lot of different programs in a lot of different theaters, and a few examples, I've got some pictures up. One is the Apache attack helicopter. Northrop Grumman develops it's called the Longbow fire control radar system. I circled it in this little figure. It tracks up to 256 targets at once. It's pretty interesting stuff. So I helped with the manufacture of that. So figuring out how do we actually build these really sophisticated, complex systems on a nice timetable so that we can actually get it out into the field to the warfighter and do it in a way that is cost effective. Another program I worked on is called SBIRS, SBIRS. It's a space-based infrared system. And at a high level, what that does is if there's a missile launch anywhere in the world, we use IR infrared tracking to pick up on the missile trail to identify the launch, predict where we think it's going to go, and then present that information to some kind of countermeasure systems that we can, take out that attack. So just some examples of what I did there. In terms of general skills, you'd be surprised to learn that I really wasn't using a lot of the more complex mathematics, for example, that I covered in undergrad. I was basically doing a lot of PowerPoint engineering. So you work on these designs, you need to be able to present them to multidisciplinary teams in a way that's digestible. So they need to be able to understand what you're talking about. So developing those communication skills are really important. Most of the time I'm doing pretty much basic math. I do end up doing a lot of hand calculations for some early design work, but a lot of the time you just punt it to more sophisticated software systems. And that's just because as designs get more complex, you really need computers to help you manage all of the details and all of the complexity. So you pick up skills like CAD, computer-aided design, or FEA, finite element analysis. These are just ways of simulating what a real-world environment might be like on your products or designs. And these are things that you can pick up in undergrad and or on the job working as an engineer. But I'd say the most important things that you would learn out of an undergrad education in engineering is critical thinking and then basically learning how to look stuff up. Most of the time when I was working at Northrop Grumman, myself and all of my colleagues, we all had textbooks just at our desks. You don't have to memorize endless equations. You just have to generally know what concept you need, and then you just go look it up in a book. It's that simple. So don't use that method for like exams in class, but you do want to study. But for the most part, when you're out in the real world, you're not expected to have everything memorized. So as a quick example of why some of this critical thinking is important is not the same solutions for one problem may not be applicable in another case. So I put a little question on the right-hand side, which if I move my little Zoom window, I can read it. Why can't we cool electronics in space the same way that we cool our computers here on Earth? And I'll just answer real quick so we can keep this moving is, well, the main reason is the traditional way we cool our computers is with fans. And fans, as you may know, blow air. Well, there's no air in space. So as you can imagine, electronics, they can get really hot, but they also don't like it when it's super, super cold. So space flight designs are actually really interesting because you can't just expose your electronics to the vacuum of space. Everything will freeze and break. So when something isn't operating, you actually put heaters on your electronics to keep them warm so that the materials themselves don't crumble. And then when the electronics turn on and they start to heat up, we use other cooling techniques. You'll learn there are three main types of cooling: conduction, convection, and radiation. Conduction is by touch, and that's what we mostly use in space. So we have contact materials that pull the heat away, and then we can dump that out into into the vacuum, but we can't let our electronics specifically touch the void. So just interesting questions that come up every day when you're working in an engineering field. So some of the stuff I work on now, as a PhD student, I'm really back in more of an academic setting. So a lot of the stuff that I do is I read papers, I do research, I write papers, I do more research, I present at conferences, I do more research, and then if there's time, I get to eat and sleep and do all that normal, take care of yourself stuff. But a PhD program is very highly focused in a very specific area of a specific discipline. I mean, you're really, really narrowing down the scope. So those who do a PhD program, they have very specific career goals or very specific interests. And you may have noticed from my little timeline, I worked in industry for 8 years before coming back to school, which is not super common. But it was very necessary for me because I had no idea what I wanted to go into. Specifically, when I finished my undergrad degree, I wanted to just get out there, get some work experience. And then if I found something that I'd be more passionate about, then I could go tackle that. And that's what I've been doing here at Georgia Tech. I've mostly been looking at flexible electronics, wearable tech. There's a little picture that I have here in the corner. This is from a company called DuPont. They produce a ton of different materials, but one of their material product lines is called Intexar, and it's basically this emerging field called flexible hybrid electronics. So what we're doing is combining the traditional electronics industry where we make circuit boards, for example. If anyone's seen a circuit board, just picture it in your head. It's like a rigid card with components on it and like metal trace lines. We're combining that industry with the printing industry because printing technology has gotten so advanced that we can print pretty high density, high detailed designs like circuit designs using exotic materials like metallic inks. So now you can print a conductive pathway between components, and you can do it on a flexible material like paper or certain types of plastics. And these are very compatible with textiles that will be used in our clothing. So now you can take something like a heart rate monitor or a pedometer or a GPS and literally just print that onto your clothes. So the idea is in the future, you might have, and we're starting to see this emerge, foldable phones, a lot more flexible, stretchable, bendable, twistable electronics. So that's what I look at now. And then when and here's some good examples. I found some nice YouTube videos of some of the things you can do with these flexible electronics. In the top right-hand screen, this has to do with human-machine interfaces. This is a gentleman, his name's Yanni. He is remote piloting a wheelchair using his brain. Researchers have developed some sensors that can pick up brainwave signals. They've translated that into commands, wrote some software to allow for piloting of a vehicle like this. So you can imagine doing something like that for prosthetics, for any number of systems. In the bottom left, this is another human-machine interface. This is a little bit more direct, where you're manually operating, for example, a robotic arm. But you can imagine this is using something like strain gauges, where it's measuring the movements in your hand. And there are any number of sensors you can use. Vibration, electrical signals, the body puts out a lot of electrical signals, or just tension, compression, that type of stuff, and use that to control machines. And on the right-hand side, this is more the realm of technology that I'm getting into with printed electronics. This is basically a stick-on patch electronic tattoo type of biomedical sensor. So this is something that, it's disposable, really cheap to produce, stretchable, adheres to your skin. The substrate there is something called EcoFlex. It's a newer material that's come out, is compatible with printing processes. And that type of sensor was used to be able to pick up heart rate, respiration, and then it's got an accelerometer in it so it can pick up your activity. And that type of data is really useful for just building up medical histories. If you have enough data from a person, you can actually, for example, if you have a history of their heart rhythm algorithm or something, you can actually use that data with some sophisticated software to try to predict heart attacks, predict strokes, things like that. So if we get into a realm of medicine where we're getting more predictive as opposed to reactive, it can bring the healthcare costs way down. Okay, so next slide. And then this is the company that I'll be moving into next year after I graduate. It's called Huxley Medical. And we're looking to leverage this kind of technology specifically for diagnosing obstructive sleep apneas and heart arrhythmias. So we're developing a printed flexible device that would sit somewhere on your chest and monitor heart rate, respiration, breathing, some activity as well, and use that data, send that to specialists who are qualified to make those kinds of diagnoses. And the nice thing about these types of technologies is because they're so cheap, they're largely disposable, and they're also very portable as opposed to something that's wired up to a big bulky machine. You can do a lot of home diagnostics, and this gets into also the realm of predictive medicine and remote monitoring that helps bring the cost of healthcare down. So that's the big overview of some of my experiences, a little bit about the types of things I've done in engineering. And for the rest of the time, I'd just like to open the floor up to questions. So thank you very much.
That's the cool stuff he's working on.
Yeah, so if you guys have questions, like please feel free to either unmute, or if you're a little nervous about unmuting, you can always put it in the chat as well. But yeah, this is awesome. This is really cool stuff.
Yeah, I know I always give like a fire hose of information, but hopefully something's stuck and maybe you have an inspired question. I actually have some sample questions, so if you don't have any of your own, feel free to just read out or retype any of these. I'm happy to answer those as well.
Does anyone here have a question? I have a question in my class here.
Sure.
Do you want to come over to the laptop?
Hey, how's it going? So, about the whole this new medical technology, I think it's going to be very useful. My dad works as an emergency ER doctor.
Cool.
I'm just wondering, when will this technology be like fully out to like the public for like doctors and nurses? Like, when do you expect all this like stuff to roll out?
Yeah, I mean, so unfortunately, this is where I have to give one of those answers of it depends. So it depends on the application. It depends on what you're looking for. It depends on if there are certain cost metrics. So for example, like there are cancer treatments that are out right now that are probably super, super expensive and not readily available to everybody because of, manufacturing processes haven't gotten to the point where we can mass produce stuff. So there are a lot of factors that are involved with, something that is at its research stage, something at an institution like here at Georgia Tech versus out in the world and available to people. I'd say a general timeline for a technology that is close, so something like what we've seen today in my presentation, anywhere from 3 to 5 years is really what we're targeting. Especially as a startup company, we don't have a finished product out being sold right now, but our goal is obviously to get there, and we can't just sit around for years not earning money. So a lot of times the startups that have taken up a research that is advanced enough and that is mature enough, and we try to convert that to the commercial world, you're looking at a 3 to 5 year window to get that out to everybody. So, but it's going to be a continuous process. So, somebody's going to come out with an innovation, or they'll make something usable in one space, and then it may take another 10 years for it to be usable in another space. So it tends to become very specific to the field, the application, the cost, all of that stuff. So we're getting there. I mean, there are examples right now. You could probably look up commercial wearable products. We as a startup company have competitors who have similar products that are out there right now. So part of the answer to your question is 0 time. Part of the answer is 5 to 10 years. It's a mix. So I hope that was satisfactory. I don't know. Do you have like a more specific, was that good enough, hopefully?
Yeah, it's good enough.
Okay.
I get that takes a lot of time and wanting to make a lot of these materials.
Yeah, I mean, I glossed over it, but in engineering, like reasons to consider STEM, Oh, did I go too quickly on this? Yeah. Here's a nice slide on why you might want to consider STEM. You have the ability to make a good impact. In general, the income is pretty good. I pulled a quick chart from the Bureau of Labor and Statistics. This is really easy to look up, but you'll see the median salaries, or the mean salary. No, it is median salaries for a lot of different engineering jobs. That's not even just STEM, but engineering specifically is pretty healthy. This is above the median household income. It's definitely above the median individual income. So that's, you can be pretty comfortable if you take up a career as an engineer. But you don't even have to be an engineer if you go for one of these degree disciplines. You can be sort of a line engineer, individual contributor. You can also go into research or academia. You can launch startups. More and more CEOs of companies are coming from technical backgrounds because of that critical thinking skills that you develop in those programs. Or you can go into something completely non-science. A lot of people get a degree and then go to law school, do patent law or something else. But all you really need is, like, you don't need to be some genius or have really good memory. A lot of it is just discipline. You need to have curiosity, that intrinsic desire to go pursue that field of knowledge. You have to enjoy, in general, building and creating new things. As I said, you want to be motivated to solve real world problems through technology. And then ultimately you need endurance, because a lot of this stuff, a new product from Apple is coming out every year, but those are incremental innovations. If you actually want to create something new, that could take years. When I was working in the defense industry, I worked some jobs that were really quick. There was literally one space job that I worked for 7 years, literally from paper concept to space flight ready material that we shipped out the door. That took 7 years. So there's a mix of timelines there, and endurance and intrinsic drive is pretty important there. And it kind of feeds into how long will it take to hit the market? Could be many years, could be tomorrow. It just depends on the product, the application, the industry, etc.
All right then.
Yeah. Other questions from students or teachers?
Anyone else have a question?
I have one. So thinking of like timelines, I mean, so a lot of these students are not going to be entering the workforce for, if they go to a 4-year college, maybe not even for 8 years or more. Any predictions for what the field might look like in 8 to 10 years?
Well, so this previous chart gives you some insight, because I think it is job projections as well up to 2026. So, it's 5 years out at a maximum. This is, and I'm not sure if this is scaled in thousands already, which would put this into millions, probably not. So let's just take these at face value. I'd say in terms of these engineering disciplines, the largest growth and demand we're probably going to see is, in general, mechanical engineers, because they're kind of everywhere. Definitely computer related fields. So computer, hardware engineering, software engineering, those types of things. I guess I'm seeing higher numbers there. Anything related to the trends that you may be seeing. So environmental is always a big thing. So whether it's energy related, whether it's materials related, trying to create new organic based materials that don't require a lot of petroleum, for example, to produce a lot of our synthetics, like pretty much all of our clothes these days, if it's not like a natural material, are some petroleum based product. So you're going to see that, but networking, communication, those are all big. I would say focus more on what your personal interests are, and then it's pretty easy to find where an engineer would fit into that.
Yeah. I know our bell's probably going to ring here in about another minute. And there it is. So if you guys have time, I'd love for you to fill out a little quick survey for us. The link is in the chat. Teachers can maybe share it with you. But I know the bell has rung and that the next class is going to start. But yeah.
Thank you. Have a good break.
Yes.